Okay. So I have one problem that you asked about, this last one.
Yeah, 6.2.
Okay. So let me share screen. Okay, so 6.2. This won't take too long, I don't think. So let me go back and look at the problem, which says right here. So it's going to say, if I have an n by n matrix with integer entries, then we want to prove it's invertible and that its inverse A inverse has integer entries if and only if the determinant A is plus or minus 1. Okay. All right. Okay. Well, let's see. So what have you thought about it at all? Do you have it?
I have, but it's like I know it has like something to do with all of it. Part of the thing I really don't understand is how to prove that the inverse has integer entries. And I'm like, I get the determinant has to be either plus or minus 1, and I'm not sure how that I'm kind of sure, but I'm not like 100% sure about why that proves that A is an invertible matrix.
Okay, so the key thing, and this kind of came up in lecture today here, is to make sure that when we're talking about this, we are sure that what we mean is within the set of matrices with integer coefficients. So if we have so maybe just let me make a comment real quick before we solve this problem. So if A is an n by n matrix with, say, rational entries, and so in particular, integer matrices are contained within that set, then it's invertible if and only if the determinant is non-zero. That's for, so in particular, if you had a matrix with integer entries and its determinant is non-zero, then it's invertible, but its inverse has to have some non-integer entries. That's all. So it's not so we know that it'll be invertible. So, and the reason for this is this cofactor formula, which I didn't quite get to, but is, I think, common in a linear algebra course and should be a part of the reading. So the cofactor formula, I don't know if I got to it or not. So it says, it gives a formula for the inverse.
Is that the one where you like take the thing and then you draw the line down the middle? Oh no, that's never mind. That's something different.
No, that's more row reduction, kind of like augmented matrix for row reduction. This is just a straight up formula. I'm not sure I'm going to use exactly the same notation as Artin does, but it just says the following thing, which is assume the determinant of an n by n matrix A is non-zero, then A inverse exists and is equal to, I take 1 over the determinant of A and I make a big n by n matrix where I put M11 here. I put sorry, I think I want 2,1 here. I have to be sure that I'm getting I think this is a transpose of what you would what you would write here. And of course you have to put a negative sign and plus. So it's a little, maybe, let me actually do this. I'll give some, actually there's something called a cofactor which is a real simple. So let me define cofactor and then I'll define the formula. Sorry, let me, just so because when I write the pluses and minuses, it looks like I'm adding entries. So I
Yeah.
don't want that to, so let's put Cij is equal to -1 to the I plus j times the ij minor. Okay, now that'll make my formula a little easier. So now I can put C11 negative C21. Not negative. I absorb the sign. Just CN1, and then going down, just so it looks like I'm switching the. So in fact, it's this 2-1. If I were to write an entry, should be in the second row, first column, not the. But it does indeed. This formula has a sort of a transpose in it.
So now I can understand why it needs to be plus or -1, because why it would imply that, because otherwise the determinant A would have 0 in the denominator, which would be a no. I see that.
Not plus or -1. So not plus or -1. So I'm not quite to the problem yet. Let me just make this clear to you, but also hopefully everyone that is listening. This formula applies for rationals. It would apply for real numbers. It will apply for complex numbers, so long as the determinant of A is non-zero. Non-zero. Now, to the problem at hand, we're talking about not one of those cases. We're talking about the case where we're dealing with integers. However, as I said, an integer matrix, so let's let A be a matrix with integer entries. Now we have an if and only if question. We have a question that we want to say that it has an integer matrix inverse, not an inverse, but a matrix with integer entries. Okay, so
Okay.
more special, if and only if the determinant is plus or -1. Right?
Yes.
So let's do one direction. So if, let's assume the determinant of A is equal to plus or -1, then applying the cofactor formula gives that A inverse is equal to plus or minus basically the matrix of cofactors. Maybe the transpose, I don't know what we call the matrix of cofactors. Right?
Yes.
And so from this, but now a cofactor, what is a cofactor? It's plus or minus a minor. And what is a minor? A minor is a determinant of, a submatrix of A.
Yes.
But those are all defined by using, addition and multiplication of the entries of A.
Yes.
And of course, integers are closed under such operations.
Mm-hmm.
So this is an integer matrix. So if we know that the determinant of A is plus or -1, then we know indeed that the matrix is an integer matrix. The inverse is an integer matrix. So now the question is the converse, right?
Yes.
Okay. So now conversely, if the determinant of A is not equal plus or -1, what can happen? You tell me.
It can equal 0.
Okay, the first thing is it can equal 0. But now if determinant, let me write it this way, then either either 1, determinant of A equals 0, or 2, determinant of A
It'll equal something else, but then that'll produce a rational multiplier.
Well, hold on, be careful
Sorry.
there. It will equal, so it's not something else. So it's certainly not 0, 1, or -1, but what is it going to be? Like, what qualitatively can you say about
It about the determinant, it won't be oh my gosh, what's it called? It won't be an integer.
it? Hold on.
Oh, sorry.
So are you sure? So remember, A, what did we start with? A is a matrix
Yeah.
with integer entries.
Okay.
So what do I know about its determinant for sure that we just used here?
That it's going to be plus or -1.
No.
Oh no, sorry.
Well, so we use that here, but we had to add an additional, we had to kind of assume that was, but I'm just saying, if we used a fact about that wasn't related to plus or -1 determinants, we use, if I have an integer matrix and I take its determinant, what can you say about it? Just generally speaking, forget about anything else.
You take its determinant.
Let's say I have, will I get, pi?
No,
Will I get 7/2?
no.
Why
Maybe.
not?
Actually,
What
no.
do I, huh?
No.
So what can you tell me that that I will get? I mean, not a specific number, but qualitatively. Sorry, I'm being vague, I know.
I know. So you're saying if I take the determinant of an integer matrix,
A matrix with integer entries, yeah,
yes, then the determinant will be an integer?
correct. That's what I'm looking for, yeah.
Okay.
It will be an integer, and we use that here when we said that these cofactors all had to be integers, because we said, okay, well, they're determinants of integer matrices, they're minors, so they of a particular matrix, so they have to be integers. So we use that fact, and so what we know about this determinant, because A has integer, this determinant here, okay, oh, sorry, this determinant here, well, we're gonna assume that it's not equal to plus or -1, but because A has integer matrix, integer entries, we know it's either 0 or it's not 0 plus or -1, but is an integer. Okay.
Okay.
So, and that's an important thing that we want to observe, but is an integer. Okay.
Okay.
Now, why do I say that? Well, because what happens, so now what are we trying to prove? Let's backtrack a second. We're trying to prove that if determinant of A is not equal to plus or -1, then it does not have an integer entry inverse matrix. There is not an integer entry inverse matrix. So we're assuming that it's not plus or -1. If the determinant of A is 0, what can you say?
That it's not invertible.
Correct. So in the first instance, first case, A has no inverse period. That's in the book. If you want, you can look for the appropriate proposition to cite.
Okay.
In the second case, case 2, what do you know? Well, if determinant of A is not equal to 0, it does have an inverse by what was said above. But appealing to this formula is going to be unpleasant, very unpleasant.
Okay.
I would not appeal to this formula at this point. And the reason is because who knows what these integers are? Maybe they're all divisible by the determinant of A. Maybe when you bring that 1 over determinant of A in, you still get integers in all of these entries. I don't know, right?
Yes.
Those are complicated formulas going into those things. However, you have something a little more appealing that you can use. In case 2, if, well, in case 2, let's put it this way. We have that the determinant of A inverse by a proposition in the book, which I don't remember the number of, but you can look it up. It's not hard to show. And we cited it in class, is equal to the determinant of A inverse, or if you want, 1 over the determinant of A.
Okay.
And which is not an integer. Right?
Yes.
Because we know that it's not, we know what this is. This is an integer, but it's not plus or minus 1, and it's not 0.
Mhm.
So it's like 1/2, 1/3, 1/4, right? Or a
Yes.
negative thereof,
Yes.
right? Those are not integers. So this is not an integer. But therefore, we know that if we have an integer matrix, we take its determinant, we get an integer. So therefore, A inverse is not an integer matrix.
Okay.
And that's it. So in one way, it's easy, it's really helpful to use this formula, this cofactor formula, but for the purpose of the other direction, the converse, I would say it's just not a good idea to use. Better to
Okay.
use this kind of property of inverse matrices.
Wait, so I'm just really confused about how you saying that the determinant of the A inverse equals 1 over the determinant of A, which is not an integer.
So the reason is, which part are you not confused, or which part are you confused about?
I'm just confused about why like 1 over the determinant of A at that point wouldn't be an integer.
Because we're in case 2.
Okay. Which is but the determinant of A is an integer.
Determinant of A is an integer, but 1 over the determinant of A is
Not an integer.
So
Okay,
2
because
is
it has to be an integer, but it's not.
well, the determinant of A is an integer. That's okay. That's fine.
But the inverse isn't.
But the inverse matrix of A has a determinant that is not an integer.
Okay, that makes
It
a
means
lot
that
of sense.
the inverse matrix of A does not have integer entries.
Yes.
So that's what we're showing. Sometimes you would refer to this as the contrapositive of the logical statement. So we're saying, okay, if determinant of A is plus or minus 1, then we have an integer inverse. If the determinant of A is not plus or minus 1, then either we don't have an inverse or it's not an integer matrix. So
Okay.
that gives us an if and only if statement. Is that logical issue clear?
No, that makes sense now. That makes sense.
Okay.
Yeah, that makes a lot of sense now. Yes, that helps a lot.
I mean, you can do a simple example too if you want. I mean, which might be so just to illustrate the point. So if you look at an example like, I don't know, like 1, 2, 2, 2 or something, right? If we take the determinant of this, you'll get 2 minus 4, which is -2, right? And so now if you try to, you can apply this cofactor formula here, and just, you get a 2, a 1, a -2, and a -2. This is the matrix of cofactors, right? However, it's not, if I multiply, let's call this A. If I multiply A by this, I'll get something diagonal with -2 along the diagonals. And so in fact, I need the inverse itself is -1/2 of this, which is going to be, -1, 1, 1, a -1/2. So you'll have one entry has to be rational, right? Because and this will have a determinant that's like -1/2. There's no way I could get a matrix with integer entries that has determinant -1/2, right? It has to be an integer.
Yes,
That's it.
that makes a lot more sense now. That really helps.
Cool. Well, I'm glad it could be helpful. Looks like, thank you for asking the question. Hopefully this helped other people in the class, and I'll post this along with the lecture momentarily. But have a great Labor Day weekend.
Thank you. You too.
All right.